In the previous episode, we saw that a current carrying loop, if you have a current just going in a circle and that current has some area, that loop has some area A, then it acts like a very tiny magnet. And so it has what we call now as a magnetic moment. And that magnetic moment is given as I times A, and you can put a small n vector, and this n vector is basically given by right hand rule, where you use your clasping fingers or the curved fingers to show the direction of the current, and the thumb represents then the direction of the magnetic moment. And this is what we saw last time, and we saw that this is true because it generates exactly the same kind of a field. So that was a thing, right? But then towards the end of it, I was telling you maybe that's where magnetism comes from, even inside a magnet. But then the question comes, well, if that is true, then is there a current carrying loop inside a magnet? Where does it come from? Well, it comes from the atoms. You know that inside atoms, so here are the atoms. So we know that inside an atom, we have two things. Our modern theory of atom tells us that there's something called as the nucleus, which basically contains positive charges, charged particles like the protons, and you have these neutral particles called as the neutrons. And then you have these electrons, which are going around in circles, like so, and they're not really going around in circles. We know that today that the theory is a little bit different. We need quantum mechanics to understand that. But anyways, we're going to treat them as classical particles. Imagine these are these tiny electrons going around in circles. And if the electrons are going around in circles, then they're charged particles going around in circles, and that constitutes a current. And you know what? That is responsible for a magnetic dipole moment. And the goal of this episode is to try and figure out the dipole moment of an electron loop. Okay? So let's consider something very simple. Imagine we have the nucleus over here and a single electron, okay? A single electron going in a circular loop, like so. And let's assume that the loop has a radius r, and we'll assume that the velocity of that electron is v. Okay, it's moving with the speed v. My goal is to calculate what is the magnetic moment of this electron loop. And we're going to assign mu, not m, because we're going atomic at a small scale. Alright, so mu is going to be easy to calculate. It's just going to be the current multiplied by the area. The area is easy. It's just pi r squared. But what is the current? Current is defined as the number of charges that flow through a given cross-sectional area or through a given area per second. So I just have to find out through a given area. So for example, if I consider a small tiny area over here, I just have to find out how much charge flows through that area per second. Okay? To do that, let me use an analogy. Imagine there's a runner over here, and he's running around on a track, and the track is say 100 meters. And he runs at a tremendous speed, okay? He runs at a tremendous speed of 500 meters per second. If I were to hold an area over here and ask you, how many times is he going to pass through that per second? Well, I'm pretty sure you know what the answer is. You see, his speed is 500 meters per second, and it's for that reason, he's going to make 5 rounds per second, isn't it? And so you would say, well, in 1 second, he's going to pass 5 times, okay? You say 5 times he passes per second. And that number 5 you got by just dividing 500, that's the speed, by the length of the loop. Well, we're going to do something very similar over here. If I want to calculate how many times electrons pass through this area per second, I just have to divide the velocity of the electron by the distance. You get that? By the distance it travels, and that's the circumference. Okay? So the number of times electrons passes per second is just going to be, I'm going to call it as f. F stands for frequency, because that's actually how frequently the number of times per second is called as frequency. Anyways, and that frequency is just going to be v, that's the velocity, as you can see over here, that v That's how many meters is traveling per second divided by how many meters he has to travel per loop. And that is just 2 pi r. That's 2 pi r. Okay? But current is the number of charge, or number of coulombs per second. I now know how many electrons or how many times electrons passes per second, but I want to calculate how many coulombs per second, you know? Well, if for example, if electron were to pass 1 time per second, then the current would be E, because, you know, E coulombs pass in 1 second. If electrons were to pass 2 times per second, then the current would be 2E, because 2E coulombs pass per second. But if electrons are passing so many times per second, and therefore the current is going to be so many times, whatever this number is, whatever this F is, F could be 2 or 10 or 1000 or whatever, times E. And so the current is just E into V divided by 2 pi r. Okay? So I can now substitute the area over here. And I can also substitute the current over there. And that gives me the magnetic moment. And so the magnetic moment is just going to be the current, which is EV divided by 2 pi r, times the area, which is pi r squared, which gives me pi cancels and r cancels over here. That gives me EVR divided by 2. And that turns out to be the strength of the magnetic moment. But that doesn't sound very interesting, right? Well, I can make it a little bit interesting by multiplying with the mass of the electron and dividing by the mass of the electron. I'm going to lose a subscript, it's not needed. So this is the mass of the electron. So I'm going to rewrite that over here. So let me write that over here somewhere. So mu is, I'm going to combine E by 2m together. And what we get now is an MVR. And if you remember your classical mechanics, MVR is what we call as the angular momentum. And this is an important equation to remember. This is going to tell you something. What does it tell you? Well, if you don't look at the atomic scale, then if I ask you what creates magnetic moment, you just say, well, a current loop and some area. That's what creates a magnetic moment. That's what it looks like at a macroscopic level. But what we see at a microscopic level now is that what creates a magnetic moment is actually angular momentum. This is angular momentum. And to be precise, this is the angular momentum that is associated with the orbit, which is the only thing I'm calculating over here. So it's better to say it's orbital angular momentum. O stands for orbit. And so at the atomic level, it turns out that the magnetic moment is due to the angular momentum of the electrons. That's amazing, isn't it? It's this tiny angular momentum that creates the magnetic moment. Amazing. And this constant over here is a universal constant. And that universal constant over here, you can calculate its value. I don't want to do that right now. But you can just substitute the value of the charge on the electron and the mass of the electron. You get that. And that's called as a gyro magnetic ratio. It's a ratio that tells you, it's a ratio basically between the magnetic moment and the angular momentum. Okay? We could stop over here, but I would like to go one step further. So what I like to do now is go a little bit quantum. Okay? A little bit of quantum. There's something called as Bohr's theory. And Bohr's theory tells us that the angular momentum of an electron cannot be anything it wants. Inside at least a hydrogen-like atom, or inside an atom which has a single loop of electron, we can see that the angular momentum of an atom turns out to be, according to Bohr's theory, an integral multiple of h divided by 2 pi, where h is called as the Planck's constant. So this guy is called as the Planck's constant. And n is just a number or an integer. You can't ask me where it comes from. It's what we call as Bohr's theory. In fact, Bohr himself had no clue where it comes from. But quantum mechanics tells you that this turns out to be true. Eventually, we're going to learn about this when we dive deep into the atoms. But anyways, long story short, it tells us that the angular momentum cannot be any number it wants. It has to be an integral multiple of some factor, which is h by 2 pi. And that goes against our daily intuition, because angular momentum is basically how much orbit an electron has. And we classically tend to think that, that doesn't have any restriction. We can choose whatever orbital motion an object must have, but at the atomic level it turns out not to be so. Okay? So that's the reason. So for this reason now, what we understand is the magnetic moment must also be quantized. You see, because magnetic moment depends on angular momentum, and it turns out angular momentum is quantized. This tells us that the magnetic moment must also be quantized, alright? So the magnetic moment mu, we can write in the final form now, it has to be n times E divided by 2m into h divided by 2 pi. Okay? And that can be written now as another universal constant. And that universal constant represents the basic magnetic moment that the orbital motion must have. And that basic magnetic moment is called as mu b, which we call as the Bohr magneton. Bohr magneton. It's got Bohr in it because, it arises from Bohr's theory. It's just telling us that the magnetic moment of an atom, if you only consider its orbital motion, has to be an integral multiple of this number. That's all it's telling us. And this number can be calculated. You can calculate yourself because you know the values of all these constants. Planck's constant you may or may not know. You might have learned that in chemistry, but it has a value of about 6.63 times 10 to the power minus 34. It's a very tiny number. It tells us this number is actually very tiny. So that gives us an idea of how tiny the magnetic moment of a single electron loop is. It's an extremely tiny number. But materials end up having lots of atoms, lots and lots and lots of atoms. And it's possible that the material ends up amplifying all these tiny magnetic moments and eventually to create a very strong macroscopic magnetic moment, giving a very strong magnetic field. And so this is the origin of magnetism. This is where magnetism comes from in matter. Now I have just touched the surface of the subject over here, because this opens up again more questions, as in, why isn't everything magnetic? Because the pen that I'm using to write that also has atoms inside it and also has electron loops in it, right? So why isn't that magnetic? Why aren't we magnetic? So you see, the question really isn't why is a magnet magnetic, but the question must be, in reality, why isn't everything else magnetic? Why isn't that? Well, we're going to investigate that in the next episode. Alright, so stay tuned, hang on tight, more interesting stuff to come. See you next time, take care, bye.